Imagine lighting a small bulb and placing it in the middle of an endless, frozen darkness. No atmosphere, no shelter, no possibility of repair. Then imagine that light continuing to shine for nearly half a century, while traveling farther than any human-made object in history. That is Voyager 1. At this very moment, the spacecraft is drifting through interstellar space, a region so remote that sunlight is little more than a distant memory. The temperature around it is close to minus 270 degrees Celsius, only about 1 degree above absolute zero, the theoretical limit where all molecular motion ceases. And yet somehow, Voyager is still alive. Launched in 1977, the spacecraft has traveled more than 23 billion kilometers from Earth. More than a decade ago, it crossed the outer boundary of our solar system and entered interstellar space. Even now, after all these years, it continues to send signals back home. It still talks to us. That alone seems almost impossible. How can a machine designed in the 1970s continue operating in one of the harshest environments imaginable? How does it avoid freezing solid after spending more than 45 years surrounded by temperatures colder than almost anything we can experience on Earth? The answer is more surprising than most people realize, because the real mystery is not how Voyager survives the cold of space. The real mystery is whether space is actually cold in the way we think it is. Most of us associate cold with winter mornings, icy winds, and frozen landscapes. But when you step outside on a freezing day and feel the cold against your skin, something very specific is happening. Air molecules, billions upon billions of them, are constantly colliding with your body. With every collision, they carry away a tiny amount of heat. The more collisions there are, the faster you lose heat. The faster you lose heat, the colder you feel. That is conduction. And conduction requires contact. It requires matter. Space has almost none. In the interstellar void, where Voyager 1 is traveling right now, there are only a few atoms per cubic centimeter. Compare that to the air in the room around you, roughly 10 billion molecules per cubic centimeter. The difference is almost impossible to comprehend. With so few particles available to collide with, heat can barely be conducted away at all. There is no medium to steal warmth from a spacecraft the way winter air steals warmth from your face. So how does heat escape in space? Radiation. Every object with a temperature above absolute zero emits heat in the form of infrared radiation, invisible light that travels outward in every direction. In space, that is the only way heat can move. And radiation is slow, gradual, and manageable. Think of it this way. In a cold room, a cup of coffee cools quickly because the surrounding air is constantly drawing heat away from the ceramic. Place that same cup inside a vacuum, and it cools much more slowly, radiating heat outward like a lamp that is slowly dimming. Voyager 1 is that cup of coffee, floating in a vacuum so deep that heat can escape in only one way. That changes everything. The cold of deep space is not aggressive. It does not attack. It simply waits for your heat to fade away. And if you can generate heat quickly enough, you survive. Voyager does not have solar panels. That was not an accident. The engineers at NASA knew exactly where this spacecraft was going. At the distance of Jupiter, sunlight is already 25 times weaker than it is on Earth. At Saturn, it is weaker still. By the time Voyager crossed into interstellar space, solar panels would have been useless, cold, dark, dead weight. So the engineers chose something else: plutonium-238. Voyager carries radioisotope thermoelectric generators, 3 of them. These devices operate on a principle that is almost poetic in its simplicity. Plutonium-238 undergoes radioactive decay, and that decay releases heat, constantly, automatically, without fuel, without combustion, without sunlight, That heat passes through thermoelectric converters, materials capable of generating electricity when one side is hot and the other side is cold. No moving parts, no switches, no maintenance required. When Voyager launched in 1977, its RTGs produced approximately 470 watts of power, enough to run several light bulbs. Modest, but sufficient for a spacecraft designed to be ruthlessly efficient. But the RTGs do more than generate electricity. They generate heat. And in the cold of space, heat means survival. The warmth produced by the RTGs radiates throughout Voyager's systems, keeping electronics, cables, and scientific instruments within their operational temperature ranges. Even the electronics themselves contribute. Every circuit that activates, every calculation that runs, produces residual heat that helps keep the spacecraft alive. It is a closed loop of warmth in the middle of an endless freeze. But warmth alone is not enough. You also have to keep it. Imagine wrapping something in a blanket so advanced that it reflects heat back onto itself. A blanket so thin that it weighs almost nothing. A blanket designed not for comfort, but for survival at the edge of the solar system. That is what covers Voyager. Multi-layer insulation is a technology made from ultra-thin sheets of mylar and captain, stacked together with layers of near vacuum between them. Each layer reflects infrared radiation. Each gap prevents conduction. Together, they form a thermal barrier that slows heat loss to an almost imperceptible rate. Voyager is wrapped in this material like a gift sealed against the universe. But here is the engineering challenge that most people never consider. The problem was not only keeping Voyager warm far from the sun, the problem was also preventing Voyager from overheating when it was closer to the sun. During the early years of the mission, as it flew past Jupiter and Saturn, the spacecraft remained relatively close to our star. The RTGs were operating at full power. The electronics were producing heat, and sunlight, although weaker than it is at Earth, was still an important factor. Engineers had to design a thermal system capable of handling both extremes, the warmth of the inner solar system and the deep freeze of interstellar space. It was a delicate balance achieved through layers of insulation, thermal louvers, and radiators that could release excess heat whenever necessary. It worked. Decades later, in temperatures approaching absolute zero, Voyager's core systems continue to operate within their original design limits. A thermos drifting through the void, engineered to survive almost anything. In August of 2012, something historic happened. Voyager 1 crossed the heliopause. You may not know that term, but it describes one of the most important boundaries in our cosmic neighborhood. The heliopause marks the edge of the heliosphere, the vast bubble of solar wind and magnetic influence that our sun projects outward in every direction. Inside the heliosphere, the sun's particles flow through space and interact with everything around them. Beyond it, the sun's influence effectively ends. Voyager 1 became the first human-made object ever to cross that boundary and enter true interstellar space. The environment changed almost immediately. The solar wind, a constant stream of charged particles flowing from the sun, disappeared. The magnetic field surrounding the spacecraft shifted. The radiation environment became dominated not by our sun, but by the rest of the galaxy, and the temperature of the surrounding medium dropped even further. Within the heliosphere, the tenuous plasma can actually be surprisingly hot. In some regions, temperatures reach millions of degrees, although the material is so sparse that it transfers virtually no heat. Beyond the heliopause, the interstellar medium is colder and denser, still unimaginably thin by Earth standards, but fundamentally different. Voyager crossed into this region and continued onward. The RTGs kept producing heat. The multi-layer insulation continued trapping it. The thermoelectric generators continued converting that heat into electricity. A machine built in California during the 1970s operating in a region of space no human instrument had ever reached, functioning almost exactly as intended. There is something remarkably defiant about that. But nothing lasts forever. Plutonium-238 has a half-life of approximately 88 years. That means every 88 years, half of the remaining plutonium decays into lead, reducing its heat output by half. The process is slow, but relentless. Since 1977, Voyager's RTGs have lost roughly 40% of their original power output. What began at approximately 470 watts now produces somewhere between 250 and 260 watts, decreasing by roughly 4 watts every year. NASA has managed this decline carefully, systematically, and ruthlessly. Over the decades, engineers have powered down systems one by one to keep the most critical instruments alive. The cameras were turned off long ago. Several scientific instruments have been deactivated. Heaters supporting non-essential components have been switched off, allowing parts of the spacecraft to cool and partially freeze as long as the core systems remain operational. It is a managed death, slow, deliberate, and unavoidable. Current estimates suggest that the final science instruments will fall silent sometime between 2025 and 2030. Some may already be offline by the time you are watching this. And when the last systems lose power, when there is no longer enough electricity to operate the transmitter and no more warmth to protect the circuitry, Voyager will begin to truly freeze. Not because space suddenly became colder, but because its source of heat will be gone. The insulation will still be there. The Mylar and Captain will still surround the spacecraft. But they can only delay the inevitable. Without the RTGs, heat will slowly escape into the void. At first gradually, then completely. Voyager's death will not be an explosion. It will not be a collision, a catastrophic failure, or a dramatic final message. It will simply be silence. One instrument going dark, then another, and finally the transmitter itself. One last signal crossing more than 25 billion kilometers of empty space, taking over 21 hours to reach Earth, and then nothing. Just silence. But here is the thought that truly stops you cold. Voyager does not stop. In space, there is no friction, no air resistance, no force constantly working to slow an object down. It is Newton's first law applied on a cosmic scale. An object in motion remains in motion. Voyager 1 is currently traveling at approximately 17 kilometers per second. That is more than 61,000 kilometers per hour. And when its final system goes dark, when the last signal fades away, when the spacecraft becomes nothing more than frozen metal and exhausted plutonium drifting through the interstellar medium, it will still be moving at 17 kilometers per second. In roughly 40,000 years, Voyager 1 will make a close approach to a star known as Gliese 445, a small red dwarf located in the constellation Camelopardalis. Not a collision, just a passing encounter. It will be the closest Voyager comes to another star since leaving our solar system. No one alive today will witness it. There will be no signal to confirm it, no instrument to record it. Just a frozen spacecraft drifting past a distant star in the darkness, carrying a golden record filled with the sounds and images of a civilization that existed briefly on a small planet orbiting an ordinary star, a fossil traveling forever. Think about what that means. Voyager was never designed to last this long. It was designed to go, to reach Jupiter, Saturn, the edge of the solar system, and continue onward. Durability was never the goal. The journey was. And yet, here we are, nearly 50 years later, still listening. Still receiving data from a machine smaller than a school bus, operating on less power than a household light bulb, in conditions that would destroy almost anything humanity has ever built. It did not freeze because we understood the cold. Not merely temperature, but what cold in space actually means. The absence of conduction, the slowness of radiation, the way heat behaves when there is almost nothing around to carry it away. We gave Voyager a heartbeat of plutonium and wrapped it in the thinnest armor imaginable. And it flew. It is still flying. When the final signal comes, and it will come probably sometime during this decade, what exactly are we losing? A spacecraft? A scientific instrument? A masterpiece of 1970s engineering? Or the last physical proof that a small, curious species looked up at the stars, built the best machine it knew how to build, pointed it toward the unknown, and let it go? Maybe the answer is all of the above. Maybe that is enough. If this story changed the way you think about the universe, make sure to leave a like and subscribe to the channel. Every signal Voyager sends reminds us how far curiosity can take us, and there are many more incredible stories waiting to be explored. And now I want to hear your thoughts. What part of Voyager's journey impressed you the most? And when Voyager finally falls silent forever, what do you think humanity's next great step into the cosmos should be? Share your opinion in the comments below. I'd love to read your perspective. Thanks for watching, and I'll see you in the next journey into the unknown.